We are going to talk about symmetrical coupler curves. And here we have a table that has a lot of coupler curves on it. What you see here are basically shapes, and the line bordering or around the shape is the path that a coupler point. This is a point on the coupler link, on a 4-bar linkage. Is the path that the coupler follows as the crank rotates. We can create coupler curves, and these particular ones being symmetrical coupler curves, using a particular 4-bar linkage. These linkages are either class 1, class 2, or class 3. If they're class 3, then the coupler point does not come all the way around and close the shape, because no link is able to rotate completely if the item is class 2, which means it's non-Grashof. By symmetrical coupler curves, we mean that for each one of these curves, or for each one of these shapes, there's a line that could be drawn, and the shape would have the same curve on either side of that symmetric line, that line of symmetry, if you will. There's also some other things on these tables that are of note. On the y-axis, there is an L1 over L2 value. On the x-axis, there's an angle gamma. And so what these help us to do is create a linkage to draw out one of these shapes, because the normal process would be that you would pick out a particular path, for example, one of these paths that you want your coupler to follow because you desire a particular action or a particular motion from your machine or from your mechanism, and then you'd want to go and then create that linkage to give you whatever path you have, whether it be something shaped kind of like a kidney bean, or shaped kind of more like a banana, or even over here we have some that are shaped like figure 8s, teardrops, all different types of shapes. And so what we're going to do now is just kind of show you how this can be done, how we can create a linkage, and then how we can even simulate that coupler curve in a software package called Force Effect Motion by AutoDesk. In this particular example, I think we'll work with drawing out, let's see, maybe a figure like, let's see, how about this figure here? This particular figure has a ratio L1 to L2, which is equal to 3.5. I'm just going to jot down some of these, so when we turn from this figure, this table, I'll still have them down. So 3.5, and again, this is a class 1 also. And then we have a gamma equal to 144 degrees. And then if you notice down here at the bottom, we have some other ratios that are important. L3 over L2 equals L4 over L2 equals BP over L2 equals 2.5. So now let's talk about how these ratios and how these values relate to the linkage that creates them. Here is an example of a 4-bar linkage that creates a symmetrical coupler curve. A symmetrical coupler curve that we see in this particular case is kind of shaped like, I guess that's kind of like an oval, and you see a line of symmetry here. And so you'll see that the shape is the same on either side of that line of symmetry. The line of symmetry can always be shown for, or it can always be found for one of these linkages when you put the crank collinear with the ground link, but extended to this side. And then if you draw a line between the coupler point and the ground link 04, that line will be the line of symmetry. Now, to create a symmetrical coupler curve, there's a few particulars that must be true for the linkage. For one, the coupler L3 and the rocker L4 must have the same pin-to-pin length. And as you see here, L3 and L4 are the same length. Also, you must put the coupler point on a circle, and that circle must be centered at the coupler rocker joint, and its radius must be equal to the coupler length. And so you see the coupler length goes out here and it touches right there on the edge. So we see that this is the center of the circle, this is the edge, then that radius is indeed equal to the coupler length. So any coupler point that's centered on a circle, whose center is at the coupler rocker joint and whose radius is equal to the coupler length, will trace out a symmetrical coupler curve. So we could have even put that point P here. So if we left all the linkage just the way it is, except moved point P to here, which means AP would go here and then come down to here, that point would also trace out a symmetrical coupler curve. However, it might not be equal to the one that we have here. You can see some of the values that we talked about previously. We talked about an angle gamma, which was on the y-axis, and we talked about the ratio L1 over L2, which is equal to 3.5 for the particular curve that we're going to draw out. You also see some metrics here, some equations, which relate this angle delta to our angle gamma and our length AP to our coupler length. And so now it's time to go ahead and look at the force effect motion application and see how we can create that coupler path that we desired. So we're going to go ahead and open it up here and create a new diagram. And since we have many of these figures, I'm just going to draw this up here, see if this is evident. These are some of the equations that I wrote down that were on that table. And notice that L2 appears in the denominator multiple times. And so I'm going to set that L2 length equal to 1 and just make all these equations work out fine. Basically, we can scale our linkage by increasing the value of our crank length. And so for me, I'm going to make it equal to 1. And so I'm going to take this tool here and draw out a 1 foot long crank. And I'm going to just say that when we see that little star there next to the 1, that basically means that we are drawing, or we've set a length that will not change. And now I'm going to draw in my ground length, and it should be equal to 3.5. Okay, so because L1 over L2 was equal to 3.5, and then I'm going to come in and set my O2 ground point and my O4 ground point there. And so I'm getting close, right? And so now I need to go ahead and draw in a AP, and I also need to draw in my rocker. And so, oops, I didn't quite get far enough on that one. I'm going to delete that one and draw it in and make sure I come all the way down to my O4 position. Now, L3, if you recall, L3 over L2 and L4 over L2 and BP over L2 are all equal to 2.5. And so I'm going to go ahead and set those distances now. And since I have a 1 for my crank, I know all of these are going to be 3.5. So 3.5 there. And I'm going to make this one also, whoops, also 3.5. And so I have all those various lengths kind of set now. And what I need to do is go ahead and draw in my BP, which is going to link me to my coupler. So that E point there is going to actually be my P point. And then also going from my A point to my P point. So now that gives me my triangular shaped coupler. If I look back here, I see that on that table it says that the BP over L2 is also equal to 2.5. So I'm going to get 2.5 equal to my BP distance. So let me make sure here. Actually, I've made an error because I said 3.5. I was confusing. I should have been using 2.5 for all of these ratios, not the 3.5. And so the L3, the L4, and the BP should all be 2.5 for this particular case. I'm going to go back in and re-establish those as 2.5. So 2.5 here and 2.5 there. Okay, and so now those have the correct length, and I have a BP also equal to that 2.5. Okay, and now I still need to go in and determine this length here. This is my AP length, and I can get that length from the table, or I can use the angles. And so let's go back to our figure and see what we have for our AP up here at the top. That AP is equal to 2 times AB times the cosine of delta. And delta is equal to 180 minus gamma over 2. And so first we'll figure out that delta. So we have 180 minus 144, which is what we have for our gamma, and divided by 2. And so what we'll have there is an 18-degree delta, and then we can use that in our AP to find AP, and we'll find then that our AP is going to be equal to 2 times our AB, which is our crank length, which is 3.5. I'm sorry, our coupler length, and our coupler length was 2.5, so times 2.5, and then times the cosine of that delta, or the cosine of that 18 degrees. And so what I end up with is an AP of 4.76. And so just to show you those calculations, I first calculated my delta, which was 18, and then that allowed me to calculate my AP, which ended up being 4.76, which was equal to the 2 times AB times cosine of delta. And so I'm going to go back to my force effect motion and type in my AP as a 4.76. Okay, and so we see that 4.76. So now our linkage is set. We are ready to draw out a particular coupler curve. Just one more time, I'm going to go back here and look at what we should see. So we should see a coupler curve that looks like this one here. We have 3.5 for that ratio and 144 for our gamma. And our line of symmetry is right there. And so going back to that force effect motion, I'm going to go ahead and move this crank to be collinear extended with the ground link, and we'll see that this should be, this is our coupler point, and this is our O4, then this is our line of symmetry. And so we'll see that as we move this mechanism, the shape that's drawn out by this coupler point will be symmetric about a line passing right through here. So I'm going to go ahead and give us a motor here, and also select our point E to be a point that we want to follow, and then I'm going to go ahead and let it go. And so we see the shape that's being drawn out for us here, and I'm just going to kind of move it down a little bit there so we can get a great picture of it moving, and make it even a little bit bigger there, and let it run. And so we see the shape being drawn out, and it is exactly like the one that we wanted from our table. I'm going to stop it here, and we see that that line of symmetry here is indeed cutting this shape into 2 equal halves. Okay, and so that's how we can go about doing a symmetrical coupler curve using the force effect motion program. I'm going to go ahead now and show you one other thing that I wanted to mention. We have actually 2 different tables. We have this table where we pulled out this particular one, but we can also use a second table which also has symmetrical coupler curves, and the difference here is that the y-axis has changed. So what used to be down here, all of these ratios now are on the y-axis, and for this entire table, L1 over L2 is equal to 2. And so I'm going to go ahead and pull off one from here just to kind of show you that either is possible. In this case, I'm going to go ahead and do one a little different. Let's pick out one of these figure 8s. Here, let's see. Let's get a figure. This is kind of an interesting one. This is kind of a figure 8. It's still class 1, so we'll still have a complete rotation, but it has a gamma equal to 288, and these link ratios over here equal to 2. And so I'm going to go ahead and write those down again so we can make sure that we keep track of what's here on this table when we turn away from it. All of those are equal to 2.0, and our gamma is equal to 288 degrees, and then we have L1 over L2 equal to 2 down here. And so I'm going to go ahead and draw this one, or design this linkage using the same technique as before. And so we'll go ahead and enter our force effect motion, and again using a crank length of 1 makes things just easy. So we'll go ahead and do a crank length of 1. Set that equal to 1, and then we'll have a ground length, in this case, equal to 2. So let me go ahead and make that a little bit better. And so we'll set that guy equal to 2. So we have a shorter ground length than we had before. It's making it hard for me to select it for reasons unknown. Well, we'll set that up in a second. So I'm going to go ahead and get my ground length 02 and my ground length 04. And then I'm going to put in my additional links. So I have my, and this angle, our angle this time is 288. So that's going to be kind of down in this range. So I'm going to go ahead and start down there. And let's see, let me first give my crank, my coupler, and my rocker. And I'm going to go ahead and set those lengths up. If we recall, we're back to our equations, that L3 and L4 BP over L2 are all equal. Oh, that's not showing up too good. Let me move that up a little bit. Okay, so L3 over L2, L4 over L2, and BP over L2 are all equal to 2. So my coupler and my rocker are going to be equal to 2 because my crank length was equal to 1, as is BP. They're all going to be equal to 2. So I'm going to go ahead and try to get all these in now. And let's see what we have. So we have 2 there. And this one should also be 2. And let me see if I can now select this guy and make it. Yes, there we go. Okay, so we have 2s for all of those. And if you notice here, our gamma is 288. That's a big gamma. If you recall where our gamma is, we'll go back to our figure and we'll see that gamma is this angle here. And so we're talking 280 degrees. That's going to put us 980, but back over in this range. So I'm going to be kind of far around, and so I'll use that to draw to get a little bit closer to where it's going to be. So this would be 180, and this would be kind of 270. So I'm back over in this range, and then I'm going to go ahead and do my AP down here. And so I am ready now to go ahead and talk about the BP length, or to specify that BP length, which would also be 2. And so we have a 2 there. And my AP, to get my AP, that's the one that requires a little bit of some calculation. So again, we go back to our figure and we say that AP is equal to 2AB, which is L3, our coupler length, times the cosine of delta. So first we'll figure out what delta is. That's 180 minus our gamma, which is 288, divided by 2. So we get a negative 54 degrees for our delta, and then our AP is going to be 2 times my L3 length, which was 2, times the cosine of that negative 54. And so for my AP, I'm going to end up with 4 times the cosine of 54. And so I get 2.35 for my AP. And just to show you what that calculation looks like. And so first we calculated our delta, we got negative 54, and then we calculated our AP and we get 2.35. And so that's enough for me to go back to my drawing and focus in on my AP and set that value equal to 2.35. Okay, and so now we have the correct value there, and we're just about ready to draw. So I'm going to go ahead and make sure that the coupler point is a point that will trace out a path that we'll be able to follow. And so there we have that. And we also are going to give ourselves a motor at that location. And what we also see, that since we did draw this with the crank, zoom in a little bit, make it a little bit bigger. Since we did draw with our crank collinear extended, we can see that our line of symmetry is going to be right here from the point P, our coupler point, through our ground length, our ground point 04. So we'll have a symmetrical kind of figure 8 type coupler path. And let's go ahead and watch it. And so there we see our figure 8 with one lobe bigger than the next, and we see that line of symmetry here where we have it going straight through right there. And we did indeed draw out what we were attempting, which was, in this case, we were attempting to draw out this particular coupler curve. And so that just goes to show that we can draw out these symmetrical couplers by designing a particular type of linkage, and we can simulate them pretty quickly using the application from Force Effect Motion.